So we will today look at what is called as decoder based implementation of digital or Boolean function. So I hope everybody is aware of what is a decoder from your digital class. So a decoder is basically a circuit which take a coded input. Say the coded input could be for example a 2-bit input, and then it will produce 2 raised to n. So if this is n inputs, sorry, it is n inputs, then you will have 2 raised to n outputs. Okay, so let's take this as a and b. So when a is equal to 0 and b equal to 0, you will have one of the line which is say I'll go to call it as m0, m1, m2 and m3. Okay, so depending upon the value of a and b, you will have so this is basically 2x4 decoder. Okay, just for simplicity I'm taking a decoder with a smaller number of inputs and outputs. So you can have 3x8 also, because 8 is 2 raised to 3. So in a similar fashion you can discuss that also. So if you write the truth table of a decoder, it will take 2 input, and inputs can be 0 0 0 1 1 0 1 1 etc., and the 4 outputs, say m0, m1, m2, m3. Now the output can be of 2 types. It could be active high output or active low output. So if I am taking the case of active high outputs, then whenever the input is 0 0, m0 will be 1 and the rest will be 0. And if it is 0 1, you will have m1 to be 1 and the rest will be 0. And similarly, if the input is 1 0, then m3 will be 1 and the rest will be 0. Okay, so this is basically the function of a 2x4 decoder. Okay, similarly, when it is 1 1, you have m3 equal to 1 and the rest will be 0. If you are taking an active low output, so then m0, m1, m2, m3. So if it is active, so this is an alternative. When you buy a decoder chip, it could be either active high output or active low output. It will be just the complement of what you had for active high output. So this will be like whichever is the input combination that is coming, that will be 0 and all the rest will be 1. Okay, so sorry, this will be 1 and then 0 1 1 and then 1 1 0 1 and then 1 1 1 0. So this is the case of active low. If you have a decoder, you can use this block. So this is an entity which is very standard. So you can, if you have these standard blocks available with you, then you can use it for the purpose of generating any Boolean function. So a particular Boolean function is given to you and then you can generate. So for example, let's again consider the case of a full adder. So a full adder will have the truth table as I have discussed yesterday. So this is an example implementation of full adder using say 3x8 decoder. Alright, so to start with, you should have the Boolean function written, and it is more convenient to write the Boolean function. Say for sum, you have the min terms. So you remember the min terms we write with a sigma notation. And what are the min terms which are present? We have sum equal to 1 when any of the input is 1, or when there are basically odd number of input bits are 1. Okay, so S is basically a function of 3 inputs. So if I give that detail, I can probably write it as A, B and C. So S is equal to I will list the min terms which are present: 1, then 2, then 4 and then 7. So these are the min terms which are present. Similarly, C out or carry is also a function of these 3 input variables, and so the carry will be 1 when any of the 2 are 1, the carry will be generated. So that will be basically 3, then 5, 6, 7. Okay, so these are the carry min terms. Basically these are the min terms. So now we have a line corresponding to each of the min term at the output of a decoder. So if you take it, in this case there are 3 variables, input variables, so we have to take a 3/8 decoder. So there are 3 inputs, they are A, B and C, and there are basically 0, 1, 2, 3, 4, 5, 6, 7. So these are the min terms that are available. M0, M1 up to M7. So whichever min terms are present, basically we need to write it as a sum of all these min terms. Okay, so that's very easy. If it is a active, I am assuming again active high output. So this is 3/8 decoder, active high output. So you do one thing. What are the min terms present for sum? You have 1 present, so M1 you have to take, and then M2 also we need, then M4 we require, and then M7 we require. So you connect all this to the input of a OR gate, and that will be basically your sum output. So by using decoder and OR gates, you can generate in any SOP form Boolean function. So Boolean functions can be expressed as SOP form, in SOP form, or sum of the product form, or you can say this is canonical SOP form. So you can implement any canonical SOP form in a very straightforward manner. You just need to use a OR gate to combine all the min terms which are present in that particular function. In the similar way, if you want carry out, so then you need to pick up those cases or those min terms, 3, then 5, 6 and 7. So there are 4 min terms here also. Okay. So this is our carry out. So how easily we can implement any Boolean function? If you have a appropriate decoder then by using additional, depending upon the number of output functions, you use that many number of OR gates, and each of the OR gate will have number of inputs which correspond to the number of min terms present in the canonical SOP form of that Boolean function. So this way we can implement. Now this approach is very convenient for designing memory, and there is a memory which is designed in this fashion, which is called ROM, or read-only memory. So this architecture is what is used for designing read-only memory, because you can look at this as in the form of a memory. Now, so the one which we have here, you can look at it in two different ways. One way is that you look at it as a circuit for two Boolean functions: the sum function, which is a Boolean function in 3 variable ABC, and a carry out function, which is also a Boolean function in 3 variables. That's one way of looking at it. But another way of looking at it is like this is a memory which can store basically 8 words, and each word is of 2-bit length. Okay, so for memory, the important characteristics, we will come back to memory later also, but right now I am talking about only one kind of memory, which is called the read-only memory. So memory is specified by two things. One is it has storage capacity of a number of words. Okay, number of words that can be. So it is characterized by the number of words that can be stored. And the second thing that characterizes any memory is basically the word length. Okay, the word length. And what is the word length? Basically, it is the number of bits in a word. So for example, there could be 8 bits in a word, and you can store say 2 raised to 10 number of such words. Okay, so which is like 1048 words. Okay, so these are like common. So when you look at the specification of any processor, every processor will have some ROM inside, or microcontroller it will have some ROM inside, or even your mobile phone has some ROM inside, which is able to store some amount of data inside. And the amount of data in terms of bits, if you want to specify, it is basically so if I say that this is basically equal to n and this is equal to m, then n by m bits it can store. So that is the storage capacity, is the storage capacity. Okay, so in the above circuit, if you look at in this fashion, so we are basically storing 8 words, and each word is of 2 bit. Okay, so it is 8 into 2, so 16 bits can be stored. And in order to see what is the data stored in each location, so there are 8 locations, and each location is addressed by an address. So ABC can be treated as an address. Okay, so ABC, these are the 3-bit address that you give to the memory, and so that will basically take out the data that is stored. For example, if you give 0 0 0, what it will make, the decoder will make the output of the first output line to become 1. If it is active high output, the first output line will become, so this is active high output I have mentioned here. So the first output line will become 1 and all the rest will be 0, and therefore the S is going to be 0, because all other outputs line from 1 to 7, they are going to be having 0 there, and therefore all inputs to the OR gate is 0, therefore S is equal to 0. Similarly, C out will also be 0. So it means that we are storing 0 0 at the location corresponding to the address ABC equal to 0 0 0. Okay, so that's basically like the truth table. Okay, so you give a different combination of ABC, you have S equal to 0 and C out is also equal to 0. Then 0 0 1, if you give then the data that will come, so if you give say 0, A equal to 0, B equal to 0, so if you give this address, what will happen is that this will become 1, and so therefore S will be equal to 1 and C out will be equal to 0, because we are not connecting to that one for C out. So the data that is stored in the address location corresponding to 0 0 1 is going to be 1 0. So this way you can look at it. So either you can look at this circuit as the implementation of a Boolean function, or you can look at it as a read-only memory. And the reason why we call it as a read-only memory is because these connections, once you make it, they are going to remain for ever. Like the processor will have a ROM which has some data inside which you cannot change. You are not able to change it because they are permanently stored there. And because these connections are where the storage is made. Okay, if there is a connection, so that amounts to storing 1. If there is no connection, that amounts to storing 0 in that particular location. Okay, so now this is very convenient in order to design what is called as PLDs. What are PLDs? We have studied this in your digital electronics course. Anybody knows the full form? Programmable logic devices, PLD. Okay. Now PLD is basically an architecture where you can basically create certain connections, okay, and implement Boolean functions. Okay, so there is a standard architecture. So there are various kinds of PLDs. So the different kinds of PLDs are basically one is called ROM, which is basically programmable ROM. ROM I have already said, read-only memory. Then you have PAL, which is programmable array logic. Then 3, that is PLA, which is programmable logic array. Okay, so these are 3 kinds of PLDs. So what are PLD? PLDs are basically standard architecture which is available to you in the form of a chip, and then you are able to basically make connections inside, okay, according to your requirement. You may want to implement a particular or generate a particular function, so you use this standard architecture, the chip containing standard architecture PLD chip you will take, and then you depending upon whatever function you want to make inside that chip, okay, you make certain connections inside, okay. That's what is referred as programming. So programming is basically make or break certain connections. So certain PLDs are such that you break the connection which is already there, okay. Or the other type of PLDs are like you establish a connection according to your, so already there is no connection to start with, and you make a connection wherever you want to have a connection. So, and depending upon the way you program it, it will basically give you an output which is your required function. So these are standard architecture which are available to you, and they go from simple PLDs to complex PLDs, okay. So what I have listed is basically 3 types of PLDs, but now if you look at PLDs in terms of the complexity, so depending upon the complexity of the function that you want to implement, you may need to go for an architecture which is more heavy in the sense there are more larger switches available where you can make or break connections, and that way you can implement complex functions, okay. So but if you are interested in, say, simple functions, you don't require a very big architecture. With a very simple PLD architecture you are able to, so PLD in terms of complexity, it could be, you know, so this is another classification you can have, which is called simple PLD or SPLD, or complex PLD or CPLD. So probably you might have heard the term CPLD. It is very common. So we will come into that, but let us first discuss about PROM. So PROM, if you take the full form is programmable ROM, it will have basically fixed and array. So all of this has basically an AND array and an OR array. So let me specify that first. So all these PLDs have an AND array as well as an OR array, okay. So there is an AND array as well as an OR array, okay. So let's look at how is the programmable ROM look like. So PROM architecture. So PROM will have fixed and array and programmable or array, okay. So we have already seen the decoder and OR gates can be used to create any Boolean function. So the philosophy is the same, but we are bringing in programmability into the that architecture. So that's the only difference. And so if we have, say, for example, a 3 input, then the PROM architecture will look like, in that case, you have say A is one input, so you can generate A bar, then another input is B, generate, okay, there's a NOT here, so that will generate your B bar, and then you have C input and you have C bar. Okay, so this is basically the input and its complement form, and then comes the OR array. So AND array. In the AND array, first comes the AND array, and in the AND array what happens is basically you have fixed connections. So the connections will be, you can represent these connections in a symbolic fashion. If I do it in a symbolic fashion, what we usually do is basically draw a line like this, and then we are basically looking at the circuit inside a decoder. Okay, so this is same as the circuit that is inside a decoder. So for example, you need connections with A bar, B bar and C bar. Okay, so that is going into an AND gate. So what this actually means is basically you have a 3-input AND gate, and one of the input is A bar, another input is B bar, another input is C bar. So this is actually what it means, but right now we are showing it in a symbolic fashion, but you need to understand that this representation means that you have a AND gate with 3 inputs. One of them is A bar, another is B bar, another is C bar. And the implementation of this function, you can do it in various ways with the use of transistors, etc. Okay, so and what is the output of this AND gate? The output of this AND gate is basically M0. So similarly, you can go to the next. So this is an array of AND gates. So this is the second AND gate, which will give us basically M1. And how do you generate M1? You need to make connections with A bar, B bar and C. So that will give you so this way you can generate all the 8 minterms. So how to generate M2? You should have B1, then C bar and then A bar. So it is 0, 1, 0. Similarly, M3, so that will be M3 is basically 1, 1, so B1, C1 and A bar. Okay, so this way you continue. M4 is basically 1, then 0, 0. So you don't have any control in this making connection or removing connection. This part is not programmable, it is fixed. So all these AND gate inputs are connected and it is available to you. You don't have any access to make or break those connections. So then 1, 0, 1. So that is what I mean by fixed AND array. And then we have 1, 1, 0. We have one more. Okay, so that is 1, 1 and 1. Okay, so we have all the minterms now available. Now come the programmable part. So we have completed the the AND array. So this is basically the AND array. An array of AND gate is here, and now we we would require an OR array, and the number of gates or OR gates in the OR array depends upon the word length. Okay, so we will have say if there are 4 bits in the words that are stored, then you will have 4 lines, and these are, so symbolically we show it as so these are the OR gates which are symbolically shown here. The inputs are shown very symbolically. Now each of this so it will have a large number of inputs. Each of the OR gate will have a large number of inputs, and you need to decide whether which all input you need to connect to these horizontal lines. So that depends upon the functions that you want to implement. Okay, so for example, if so this is F1, F2, F3 and F4. So let's say F1 is basically A B bar plus B C D. Sorry, D is not there. So let's say ABC. A B bar plus ABC. So this is your function that is given, and F2 is A bar B bar C plus AC, and F3 is, let's say, A bar B bar C plus A B bar. Okay, so let's limit with 3 function. So I have taken some common parts here. So A B bar is here also, and A bar B bar C is here also. Okay, so for simplicity I'm just removing one of this. Okay, so depending upon the number of bits in the word that you want to store in the ROM, you will have that many number of these vertical lines. Okay, so if this is the function that you want to implement, so we need to program the PROM. So this so the programmability is only in the OR array. Okay, so it has fixed AND array. Here connections are already made and it is available to you, nothing can be done about it, but programmability is only in the OR array part. So suppose you have this function, how will you proceed? Can anybody tell me what is the way to proceed? These functions are given like this, and some of them are repeating, and how is it that you are going to program the OR array? So that is what you need to understand. Can anybody give me an answer? Yes?
So they have to bring all the elements C every term.
For example, F1. So how will you program the connections here? What we need to do? What is the first step? AB bar plus ABC. So where we should make the connection? Here. There are 8 positions where you can either make connections. Right now there is no connection. Assume that there is no connection. You are asked to make a connection. Depending on
make a connection at M7.
M7. Okay. So I'm making. Oh, sorry. So let's make a connection at M7. Right. Then
we need to take a separate connection for the AB bar.
So how do you do that? We cannot do anything here. Okay. This is fixed part. All you can do is here. Here is where the programmability is there. So we have chosen one output for F1, another for F2, another for F3. So ABC is now included. One of the input is connected to M7, which is ABC. That is right. But what about AB bar?
So we can write AB bar as B plus C bar. So we can get AB bar C plus
Right.
A
A B
C
bar
bar.
C bar plus A B bar C, right?
Yes, sir.
Yes. So there are three minterms which are actually present. So there will be three connections. So one is M4, right? And the other is M5. Everybody get that? Similarly, you can do this also. So A bar B bar C plus A B C plus, or A B bar C plus A B C. So here also the ABC is there, then M2 is there, 5 is there, M5 is there, and then 001, so which is here. Okay, so similar thing you can do here also. Then it will be A bar B bar C, which is 1, and then A B bar C bar plus A B bar C. So this is 001, and the next is 100, 100, and the last one is 101, which is this. Okay, 5 is 101. So that's how we program it. So we make connection wherever we want it according to the output functions that we intend to make. Okay, and so there is a complete access to making this connection. So some of the prompts are such that you need to make connection wherever you should. The other type of programmability that may be available to us, maybe already connections are there, but you need to break those connections. So initially everything is connected, but you need to break the connection wherever. So that is like removing the connection from all the remaining places. Okay, so that is another way. Like there may be something like a fuse which you need to blow it up basically. So other is like anti-fusing. You basically join together. Okay, so there are more versatile ways of doing it. Like you may have a transistor between these 2 points. Okay, so the way it is going to implement those connections are of different ways. So for example, if there is a transistor between these 2 points like this, so this is intended for connecting these cross lines. So what you need to do is, if you want to connect it, you store a 1 here, you give a 1 here, so that is like making a connection. If you give a 0 here to the gate, so that is like no connections. Okay, so there are various ways in which this could be implemented. So we are not looking at the implementation part of the connection, but we are only looking at the architecture part. Later we will look at transistors and all, how it can be operating as a switch in more details. Okay, so that time it will be more clearer, because without telling the MOS function, if I say these things, so if required, I will give you some more details with respect to this establishment of connection after we discuss about the transistor. So this is one way you can proceed. Now let's go to the second architecture, which is basically say let's PAL, okay, which is programmable array logic. Again, this also has, all of this has an AND array and OR array, but there is difference. So here the programmability, so it has programmable AND array and fixed OR array. Okay, it has programmable AND array and fixed OR array. So the architecture is similar, or actually it is the same. Only thing is the programmability is in the AND array part. So again, so let's do this. This is another way of drawing A and A bar. So wherever there is bubble, it corresponds to complementing. Okay, so now the AND array. So let's take the same function. Okay, now the function has, okay, so these are the minterms which are present. So let me so just draw this part first. Maybe we will implement 2 of those. So these are fixed connections which are already made. So this is our OR array. Okay, and then so just like before, we had a AND array and OR array. Here also we have AND array and OR array. Now here the connections are to these 3 lines. Okay, so let's if I have to draw one more, then I need some more space. Okay, let's do it with this F1 and F2. Suppose we want to create F1 here and F2 here. So if you require F3 also, then I should have 3 more lines, and then the last 3 will be connected to F3. Okay, so that's basically the idea. So right now I will explain just with F1 and F2. So there are basically 6 horizontal lines, not 8 horizontal lines. So we have only 6 horizontal lines. So one of the disadvantage of the earlier circuit was that if you look at this circuit, there were say M2 and M3 which is never used, like M0 is never used, M3 never used, M2 never used, and M6 also never used. So we have only used M1, M4, M5 and M7. Okay, so lots of horizontal lines, and there are lots of hardware for this generating M0, M2, M3 and M5, but they are unutilized, and this unutilization of the existing hardware become more and more worse when you have functions which are of more number variable. Here only 3 variables, and therefore only half of them were not used. Maybe if you have a function in say 5 variable or 10 variable, then the unused part will be much more. Okay, the unused part will be much more compared to the used part. So that's the disadvantage. We have a lot of hardware which we have created, but then the functions that we want to implement only have a few of the terms. Okay, and therefore the remaining hardware part is basically unutilized. So that disadvantage can be overcome here because we are not having if there are say 3 for example, in this case we have horizontal lines only 6 if you have 2 functions. Okay, if you want one function, maybe only 3 would be required, and if more functions are there, then of course we need correspondingly more and more horizontal lines. And now each of these functions would be connected to either 3 horizontal lines or 4 horizontal lines or 5 horizontal lines. So that is hardware that you need to choose. Okay, so depending upon how many terms are there going to be in your function, you need to choose a appropriate PAL hardware or PAL hardware such that you could implement comfortably those functions without because if in this case 3 are required at least. Okay, if 3 are required, then maybe you need only 2 also. So even if it is 3 available, then you can use 2 of those lines. Okay, but if all the 3 are need to be used, then also it is possible. Now if 4 terms are there in F1, then if only 3 horizontal lines are there, then you won't be able to implement that function. Okay, but there are certain other variations of this PAL architecture which could be utilized in order to even implement a F1 with the 4 product terms, even though there are only 3 horizontal lines. Okay, basically you will take this F1 back to the input. Okay, so there will be, so I'll just show it here. So if suppose you want to implement say a function which contain basically F2 is basically a function which contain all the 3 product terms in F1 plus some additional term. So what you need to do is you take this F1 back, and then you will have F1 and F1 bar here. Okay, so that is just a variation of this thing. So there will be F1 here. Okay, so you can just take it here back like this, and then you will have F1 bar here, F1 bar here. So then this could be connected like this. So when you connect it, so this F1 is actually produced here. It contains 3 terms, and then all those 3 terms will be available for you here. And when you make connection for F2, you take a point from there and include all the 3 terms. Apart from that, you can add 2 more additional terms. So that way you can extend. So these are some other possibilities which are there. Okay, so now coming back to our original function. So I'll just show how to implement. So you have already gone through this in digital electronics, but that time I didn't teach you. So okay, so let's rewrite that functions here. Your F1 is basically AB bar plus ABC, and let me write F2 as okay, let me take this F3 instead of F3. Let me take, okay, F3 is basically A bar, B bar, C plus AB. So these are the 2 functions that I want to implement. AB bar is common. Okay, so now how do we implement? Okay, so let me just change this to F3. Okay, so how do we implement here? So this part is fixed, there is nothing you can do about it. The OR array is fixed, the programmability is only in the AND array. And how can we achieve this? Anybody? Hello? So this is the PAL architecture, and you are asked to implement this F1 and F3. So this is the type of question you can get also. Hello, quickly, don't waste time. Are you there or not? Yeah, tell me how to implement these functions using this PAL architecture.
Sir, if we multiply A B bar by C plus C bar, then we will get 3 products.
Okay, so you are saying that do A B bar C bar plus like before, right? That's what you are saying. Yes.
Sir.
This time we have to put these 3 terms in this n part.
Okay, so so tell me where I should connect.
So first line A B bar C bar.
So okay, so connect
N0.
Okay, so connect here. So I'm dot means permanent connection, cross means I am programming it. Okay, so A B bar C bar is what you are saying, and then similarly the other two also, right? A, then B bar C, and then ABC. So that is A B C. Now the question is it necessary to do this way? Of course you will get each of these terms here, one here, one here. So let me call this as product term 1, product term 2, product term 3. Okay, so you will get P1 here, P2 here, P3 here. Definitely you will get, but is it the best way to implement it, or is there a better way to do it? Suppose I had the fixed connection part only two lines for F1 and 2 lines connected for 2 horizontal lines are only connected with F3. Is it possible to do it? So here you see that there is 3 horizontal lines connected to each of the output functions, right? Suppose I had only 2 output lines, for each output lines only 2 horizontal lines are connected instead of 3, then will you be able to implement this?
Yes, sir.
Okay, so let me just change the architecture right now, so to make that point clear. So I'm modifying it. So what I mean to say is that so here I am connecting these two, and then of course in this case I can go for F. So this is F2 and now it is F3. Okay, suppose this is my architecture. Okay, I have only two horizontal lines are only connected to the output corresponding to F1, and we want F1 here. Okay, and F2 we want here, and these are connected to these two horizontal line, and similarly this. So I'm just going to erase all this again. So if this is what is the architecture given to you, how to go about making connection now. Okay, so this is the architecture given to you. So F3 is written here. Now let me write F2 also. F2 is basically A bar B bar C plus A B bar. Sorry, that is F3. Okay, so tell me now how to implement these functions. I want to implement now F1, F2, F3. Okay, I have changed the architecture. This is what is available to us. Now tell me whether you are able to do it or not.
So for F1, no need to connection the C for AB bar.
Repeat. I didn't get what you mean.
So for F1, AB bar, the C we don't have to connect it.
Okay, so I am guessing what you mean is you are talking about this product term, right? Are you?
Yes, sir.
Yeah. So now we will take this as our P1. So I will just remove this part. We don't need this expansion, because if you expand it, you will require 3 horizontal lines corresponding to each of the product term. Okay, but if you don't expand it, you have A B bar. Okay, so what you should do is you connect it to A and then you connect it to B bar. Okay, so you have an AND gate with only 2 inputs, A and B, and if you don't connect it, it will be this means only 2 inputs. Okay, now there may be a third input which is not connected to anything, and that should be held high. Okay, so if I give you the details, that should be held high. So I need to explain that a little bit. So if I take a portion of this and expand what is the actual way it looks like, so let me just expand all this part. So what I mean to say is that it has 3 input. So this is the AND gate. So this is how it looks like, and the moment we make a connection, okay, so making a connection means programmed connection. So one I have connected with A means I am giving here A, and the other place I am giving B means, or B bar means I am giving an input here because I made a connection with B. Okay, now I have left this open. Okay, so if this AND gate would take it as a high, then it will be okay, A B bar into 1. Okay, if this leaving it unconnected, so that's what here we have not made any connection here with respect to C, as somebody told you as here. So if we leave it unconnected, so it's basically one way to look at it is like you are leaving it at high impedance state. there is no connection with either 0 or 1, and therefore it would be treated as 1. If you treat it as 1, that is perfect. So that will be A into B bar into 1, and that will be basically A B bar. Okay, so you will get A B bar here. Another way you can think about it is like you are familiar with the idea of pull-up resistors. So what does a pull-up resistor do? So you have a resistor here. All of this input will have a resistor here, which is connected to high voltage. Same. Okay, so these are all connected to high voltage. And the moment you establish a connection with A, if A is 1, the input will be 1. If A is 0, since it is a pull-up resistor, if A is maintained as, you are establishing a connection here, okay, and similarly here also, this is with respect to A and this is with respect to B bar. So when A is 0, what will happen is that the voltage here will become 0. Okay, all the drop will be across this resistor and it will be 0. If A is 1, it will be held high. So this is the idea of pull-up resistor. So whenever we want 0, you can bring it down to 0, but if it is high, it will remain at high. So the advantage is that if you don't make any connection here, so here we made a connection, here also we made a connection, but here we are leaving it, and if you leave it, automatically high is coming here. So this is another, if you don't have a high impedance state permitted in the AND input, then you can implement it with the help of a pull-up resistor. So if you don't connect it, it will be held high. Okay, so I am just giving you the detail of this connection. Okay, so you can implement that connection in this manner. So there are 3 inputs to this AND gate, and you can either connect only one vertical line, A bar, B bar, C bar, any one, and you can leave the other 2 unconnected, or you can leave one unconnected and the other 2 you can connect, and that way you can implement this function. So I hope you are following now. So P1 will come here. So this is your P1, and then what about P2? You connect all the 3, right? So A you connect, B you connect, C you connect. So that will give you P2. P1, P2. And what about F2? Same procedure, A bar, B bar, A bar, B bar, you make connections, and C, and then the next is AC, so that is your P3, so this is your P3, and then AC is basically you connect here, A and C. Okay, so that will give you P4. Okay, now what else you do? Okay, I have already generated P3. Can I take advantage of that in any way for making F3? Yes or no? Are you following my question? I have generated P3 here, and P1 also I have generated. So this is again P3, right? A bar, B bar, C, and this is P1, which is A, B bar. I have generated those already. Now can I create F3 here using all the function? Huh? Yes or no? How? So how do you do that? No, you can't change this connection. That's the point. Here this is fixed. Okay. In a prom, these dots are fixed connections which you cannot change. So there is no way you can have access to P1 and P3 which is already generated above. There is no way you can access it for F3. So you need to generate that again. Okay. So you need to generate that again. So P3 you need to create again, like before. You need to do this. So that is your P3. Okay, so you need to bring P3 again. So there is a repetition here, which is what is the advantage of the next type of architecture, which is PLA. So where you don't need to do that. Okay, so and P1 also you need to generate. So P1 is basically a P bar. Okay, so we have generated P1 2 times and P3 also 2 times. So but still it is better than your PROM architecture, because the same function which was implemented earlier we could implement with lesser hardware. You look at the amount of hardware required here. We have only 6 lines, and in a way we are utilizing all the lines. Okay, all the 6 lines we are using, but earlier there were 8 AND array, out of which we were only using 4 of them, right? So for the half of the AND array was unutilized, and that's a wastage of hardware. Now let's go into the last type, which is PLA. So that is programmable logic array. Okay, the words are just interchanged. Earlier it was PAL, now it is PLA. The full form for each letter is same. Now the difference is this: it has got programmable AND array. This also has AND array and OR array, but it is programmable. Programmable AND array and programmable OR array. Both are programmable. Alright. So let us try to implement the same function with this. Okay. So here both are programmable. So let me just take this. Okay, so this is our function. So let me again do the drawing. So this is my A. B, C, and right now there is flexibility here also. Okay, so I am only drawing 4 lines because I know that 4 lines is enough, and there are 3 functions. So okay. So this is the architecture. Now you can program both area, the AND array input connections. You have the flexibility. For example, this AND array can have 3 inputs. This AND gate has 3 inputs, so you can decide where each of those inputs are connected. And similarly, this OR array can have 4 inputs, each of the OR gate has can have 4 inputs, and where it has to be connected you can decide. Okay, so you can see that this architecture is even smaller compared to the earlier architecture. First we started with 8 horizontal line, then 6 horizontal line. Now we have only 4 horizontal line. So can you tell me how to implement it? You should be able to implement it. It is possible to implement this given function using this architecture. Tell me. Don't waste. Yes, A B bar you make it like before, right? Yeah. So you make a connection here, A. So that will give you P1. Then what else? Next line, how should I program?
ABC.
ABC. So A, B, and C. Next. A bar, B bar, and C. So that is P2 and P3. Next. AC, right? So AC means A and C. So that will give you P4. Now what we have to do? Our programming is not over because both are programmable. OR array is also programmable and array is also programmable.
So for F1 we connect P1.
Okay, so we connect P1 and P2. Okay, so that will give you F1, and then
So for F2 we connect P1.
F2, P3 and P4.
P3 and P4 you connect.
For last one we connect
For
P1.
P3 and P1.
P1 and P3. Okay, very good. So that will give you F2 and F3. You see that the complexity of the circuit is much further reduced because we have programmability in the AND array side as well as the OR array side. But now I want you also to justify that if you leave one of the input unconnected, then how is it going to look like? So this part, can you give the details? So if I say like earlier that high impedance state will be treated as high, so some of the input if it is not connected, so there are 4 inputs to this OR gate, and if 2 of them are not connected, so let me just draw this, say F1. So we are basically connecting this to say P1, and the next one we are connecting to P2, but the next 2 we are leaving unconnected. We are not connecting to anywhere. And if you treat it as high, then we are going to have problem, because it will be like P1 plus P2 plus 1 plus 1, right? So if it is going to be treated as high, it is going to be problematic. So what do you need to do?
So ground it.
Yes, so we need to pull down it. It's not grounding it. You can't ground it because that option is not there. You can only make a connection with the vertical lines. Okay, vertical line and horizontal line, you can make a connection. So the idea is to use a pull down resistor which is connected to ground everywhere. So that is everywhere, all of them. So if it is not connected, it will be naturally connected to the ground. Okay, so everything is connected to the ground. Suppose if P1 is 1, so all the drop will be across this resistor, and the input to the OR gate will be 1. If P1 is 0, it will be 0. So depending upon what is P1, whatever that is the value of P1, that will go to the input of OR gate without problem, because there is a resistor through which we connect it to the ground. Okay. So, but if it is unconnected, we have an advantage. It will be treated as 0. Okay. So at the AND array side, we pull up the input to high state, whereas in the OR array side, we pull down. So, okay, so these resistors are pull down resistors. Okay, whereas earlier what I have shown you, so here I think I remove, here it is. So this is to some high voltage, okay, plus V. So these resistors are now called pull up resistors. Okay, so by using pull up resistors at the input side and pull down resistors, you can overcome that problem. Okay, but all of this also depends upon how actually you are going to implement this AND gate. Okay, there are various other ways in which you can implement our AND gate where these issues may not even come up. Okay, there are clever ways of doing that. Okay, so those are the circuit detail, but right now we are looking at the gate level. Okay, so now as I told you, so we have seen three kinds of PLDs, so which has some programmability, and there are other variations to it. So you can just program it once and then forever it will remain. Whatever circuit you created, that will remain. So that is what we usually called as programmable PLDs, but that is not very desirable. We should be able to erase the connections that we have made. So more sophistications are added to it. For example, if you look at PROM classification, so PROM, the symbol type we have already said, which is which can be programmed once. Okay, so that is one type. The second type is EPROM. Okay, now what is EPROM? Erasable. So here you have an option to erase every connections or disconnections that you have made. Whatever programming you have done once, you can erase it all together. So earlier type of EPROM, so this is erasable PROM, it was making use of what is called as UV light. So there will be a window on the top of the chip, something like this. There is a window, glass kind of window, so through which you irradiate UV light. Every connection that you have made in order to configure a particular circuit or a logic design inside the chip is now erased. Okay, so this is a chip which has a window to pass UV light and erase everything, and then you can program it again. Okay, so that is EPROM. And then there is a still refined version which is called EEPROM, which is electrically, so UV light irradiation and all are quite difficult. You need an UV source, etc. So later it is improved to electrically erasable programmable read-only memory. So this is applicable also to other PLDs like PLA and PAL also. So these are basically strategies. So electrically erasable means you will have a separate dedicated pin which is for erase purpose. Earlier microcontrollers, like in our undergraduate time, these EEPROMs were very common, where you will have another extra pin where you supply some higher voltage. Usually it is operating at 5 volt, but then if you give some 12 volt to that pin, everything that you have loaded into the chip, whatever connections that you have created inside, everything will be erased. So that is electrically prone. Okay. And the other is EEPROM, which is what nowadays we all use. So which is basically electrically alterable PROM. Do you know the other word for this? You don't say this word actually, electrically alterable PROM. You don't say that, but every one of you use this. Anybody? Yeah, pen drive. Okay, so your flash memory, that is another name. Okay, so flash memory is an electrically alterable PROM. Okay, so PROM means, you know, the architecture I have already told you. It has first fixed and array. It is generating all the minterms. Basically it is a decoder, and then followed by an OR array, and every time you store, basically you are changing the connections. Okay, and the details depend upon, you know, how it is implemented. It would require a special type of transistor, a floating gate MOS transistor is there. That's by using that you can basically change whatever is stored to 1 or 0, which is equivalent to making or breaking a connection. So you are able to change that arbitrarily, and it is a big success now. Even your RAM is also these days are based on flash memory. Okay, which has advantage of speed, right? Okay, so what we have seen is like the PLD structures, and then another thing I told you is that the PLDs are of simple PLD or complex PLD, which is CPLD. So there are lots of chips which are already made. So maybe we can look at say Google it and see. So simple PLD, there are some names. Simple PLD architecture. So if you search simple PLD architecture, complex PLD architecture, so there are companies which would let me see some numbers. Probably if you look with some numbers, you will get it better. Complex PLD. So yeah, a complex PLD chip will look something like this. Okay, Ultra is a manufacturer. Another one is Xilinx. Xilinx and Ultra chips are those two companies are very common manufacturers. You can see the number of pins here. All across there are pins. So okay, so unless and otherwise we give this number, I don't think we will get. So max 700. Okay, so let's look at a data sheet. So max 700 or 7,000. 7,000. So CPLD architecture. Yeah. So Ultra is now part of Intel, I think. So this is the manual for every. If you know the number, you will. Okay. You can see this. Is it visible? Is it better now?
Yes, sir.
Okay, so this is a CPLD. CPLD, as I told you, it is complex. I mean, basically, you have more space to implement a more complex function. Okay, so it has a standard architecture, and if you look at this architecture, there is a block which is shown in blue color here, and it has what is called as macro cells 1 to 16. So there are 16 macro cells. I will come into what is a macro cell in a moment. Probably this data sheet itself will have the detail of macro cell. So there are 16 macro cell in say one block named as LABA, and similarly there are many such LABs. LAB full form is some logical block, some LA for what, I don't know. Different names will be given. So some logic block, let us call it as logic block. So there are many number of them, and each logic block has here around 16 macro cells. Okay, now each macro cell you can treat it like a PLD. Okay, the PLD which we have discussed, either PAL or PROM or PLA, so that is like one of the macro cell. I mean, it has some more additions, like it would include some registers also for creating sequential circuit. So registers are basically flip-flops. Okay, so each of the output which of the OR array where we have generated the function will actually be passed through a register or a memory device like a flip-flop, and then it will be available for output, or it could be given back into the architecture. So that is why you see that there are some connections which are going back from the output. So macro cell has some 16-bit output, and it is available for, you see this connection, some of them are available to the external pins, and similarly all the 16s are available to internal routing. Routing means for making more complicated connection which cannot be contained in one macro cell or even in this 16 macro cell, you need to make them to be the input of other macro cell, and thereby achieve a more complicated function. So like I told you in a little while ago, one of the strategy you could do here, this whatever I have shown in this orange color is one of the strategies. The output of one macro cell, for example a PLD, is taken out and it is available as input to say other PLDs. Okay, so where it will be not a simple function like ABC which is an input pin, but it would be internally generated function which is available as input, and using this to create the product term will help us to establish product term that contain more than say 3 variables. Okay, so because F1 itself may be depending upon if it is coming from another macro cell, it may depend upon say DEF for example. Okay, it's a function of DEF. So but that is now brought into and combined with ABC, so that you will get a product term which contain A, B, C, D, E, F. Okay, so this type of thing can be done. So that is what is shown here. So this macro cell output, which is like PLD output, you can think about right now. So it is available for if that is the output that you want, then you take it out, and through the IO pin it is accessible from outside. But then if you want to create more complicated function, what you do is that you take that output and pass it through some switches. This PIA, which is written in the central portion, that is basically a switch matrix, where you route the inputs to maybe this macro cell or this macro cell or the other macro cell. Wherever you want to route, you can reach any of the macro cells or any of the logic block which are there. Okay, so there is a switch matrix which are in the center of this, which will decide the connections, interconnections of these logic blocks, and then so you can create more complicated functions. So basically, as the difference between a complex PLD and a simple PLD is that a complex PLD has many number of simple PLDs, okay, inside it, and then in addition to that there is a switch matrix which is for the purpose of routing the interconnection between the simple PLD. So you can think about this logic block A and logic block B as simple PLDs, and there are many number of simple PLDs. Okay, the number, how many number of them, it's not shown in this diagram. Okay, so but if you read this manual, you will see the details better and better. But the basic idea is to integrate more simple PLDs in order to make complex PLDs. Okay, so let us see if okay, another thing. So this is the macro cell. Okay, so here is the macro cell. So you can see here the input side, the AND array, all the product terms which we have discussed. This is the AND array, and then you have the OR array here. So this is the OR gate. All the product terms are combined here, and as far as I can see, there is only one OR gate here, and there are how many? The numbers are not clear, but I think 36 signals. Okay, 36 signals. So there are 36 vertical lines are here. In addition to that, there is some fed back signals. Okay, so this is like what I have shown in the orange color. So whatever is one output, that is actually fed back. Okay, so that you can integrate it with the rest and have more number of product terms. So the macro cell will have basically this type of architecture, which has an AND array, and then here OR array is not there, one OR gate is there, but this is not just the one macro cell. There are 16 macro cell in one logic block. Okay, there is 16 macro cell in one logic block, and there are multiple logic blocks, so which can be interconnected. So that's the kind of complexity that is involved. So it's a VLSI chip for sure. Okay, which can be programmed. Okay, so now the rest of the thing which I have to say is that there is a register here. Okay, you can see that there is a D or T flip-flop. Okay, it can be either operating as a D flip-flop or a T flip-flop, because D bar T is given as the input. Okay, and that would definitely depend upon some another pin which will configure it as basically D flip-flop or T flip-flop. So programmable register. So you can see that. So PRN input here is a input which you can give to the flip-flop in order to configure the register to act as basically D or T, etc. Then there is another input which is for clearing the flip-flop, and then there is a clock input here. Okay, so this triangular symbol to the register is basically clock, and then the input to the flip-flop, and the input to the flip-flop is usually given through a multiplexer. Okay, and the reason why okay, so there is a multiplexer here. Okay, so this register bypass. Okay, so either the output which is available is coming out of this flip-flop, and then it is coming through the multiplexer, or it can bypass the register and come directly. If it is a combinational circuit, you don't need any register. So if this macro cell is used, can be used to create sequential circuit as well as the combinational circuit. So if it is combinational circuit, you just bypass the register, so you take the output from the this portion, okay, the top input. So according to the select input, so there is a select input here which you can program. So if it is a combinational circuit, you bypass the resistor and take the output, okay, and this output can be connected to another macro cell, or it can be taken out to the IO block, okay. So that option we have seen in the earlier diagram. So in short, you have an AND array, you have an OR array, and then there is a possibility of taking the output back from the product term and given it as additional inputs to the AND array, so thereby enhancing the capability of increasing the number of product terms. And then you have a register. So any macro cell, we have looked at a particular series which is 7000 series, but if you look at Xilinx chip also, CPLD also, you will more or less similar architecture, whichever which I said will be there also, but of course the internal details may vary slightly, but it will also have a register. So most commonly all this register, multiplexer, AND array, OR array, and then some of the inputs are from internally generated like this, that will also be there, and then IO pins. So these are basically the macro cell structure. So any of the CPLD will have similar kind of macro cell, all this, but of course there may be some little extra detail, or some of them may not contain that. So there are various versions of it. So what we just looked at is basically the internal detail of these macro cells, okay. So now there are multiple such blocks which are which can be interconnected, or it can be its output can be taken out, okay. So if you look at the number of pins, you can see to operate on 5 volt. So altogether there is 128 or more macro cells, okay, 128 or more macro cells. It depends upon whatever is the number. We are looking at 7000. So it operates on this clock frequency. Yeah. So how many pins are there? IO pins, you can see depending upon the version, the number of IO pins are differing. So it could be up to 164 pins from 36. So it's like depending upon more and more capacity you require. So the programming of this CPLD is not easy. We have done simple PLDs, we are able to make that design, okay, what we discussed in today's class. But in order to implement a complex circuit inside this, some of the CPLDs are such that even you can implement a processor, complete processor inside a CPLD you can implement. Now to implement something like that, it is not possible manually making and deciding where OR gate should be connected, AND gate should be connected. This is not possible. So it has to be done with the software. So which software does it? The synthesis software do it, okay. So after the Verilog program is tested and verified, then you give it to the next step is, as I told you yesterday, that it is synthesis of the program. So when you synthesize it, so you can now have two things possible after the synthesis step, or the synthesis step itself will depend upon what you want to do after it, after synthesis. So going back to the steps, design methodology steps. So VLSI Okay, it's strictly digital VLSI design steps. So number one is basically RTL RTL description. Basically, where I will come to what is RTL. I have to teach you that it is basically register transfer level. Okay, this part I have not taught you in digital electronics, so I will spend some time on discussing what is RTL in the coming classes. So RTL description is where you use Verilog or VHDL or System C to program your architecture or specify your architecture. So RTL description of the hardware that you want to hardware, and then so again there is a synthesis. Sorry, after this you have a simulation. So okay, so this will pass. This will be followed by simulation. Okay, so this is RTL simulation. So once you verify the functionality, then only you go to the synthesis step. Now the synthesis step, what you do here, that means basically you need to generate the hardware connection. So if you are going to make a very new chip which is like not existing, so you are coming up with a new design, there are two ways you can do it. One is by using standard architecture and configuring the standard architecture. That's what we today kind of saw. Okay, we can take a CPLD, which is like a standard programmable architecture. Okay, so after synthesis or the synthesis step itself will depend upon how you want to have your chip, whether you want to configure a standard CPLD architecture. Okay, or whether you want to configure a standard CPLD chip. There is another thing which is called FPGA. Okay, you can have another version of something similar to CPLD but quite a different, that is FPGA chip. So these are like programmable chips. Okay, so these are both of them are programmable. The FPGA name itself is field programmable gate array. Okay, and here also there is programmable complex programmable logic device, programmable. So these are programmable chips. So okay, so the synthesis output, if you are thinking of using a programmable chip and configuring it, then your synthesis should be such that it will basically generate the chip specific circuit. Okay, so when you, for example, if you are using this particular architecture, then the synthesis software should generate a circuit which would basically mapped into this which will basically used to configure this architecture in order to generate whatever circuit that you want to make. So already a standard architecture is available. It is all fabricated and available to you. All you need to do is to make and break connections, and to make and break connection inside this architecture in order to implement or to turn this architecture into a circuit which will perform the function that you want to do. Okay, that which you verified with your Verilog code and simulated it. So whatever that architecture or whatever that circuit is, you are basically loading onto this particular chip. Okay, either it could be a CPLD chip which is now before us, or it could be an FPGA chip which is like field programmable gate array, and there are hundreds and thousands of variations of these chips. I mean, different standard architecture is available depending upon what is the capability. It could be like a DSP kind of chip, like digital signal processing kind of chips, that will require like multipliers inside, floating point additions inside. So that those are like some extra things. So for that you cannot use a simple CPLD or FPGA chip. You need more enhanced versions of CPLD and FPGA chip. So so whatever is that model of the FPGA or CPLD, you take that, and the synthesis software should support the loading of those chips. Okay, so usually when a company like Ultra is a company that manufactures CPLD and FPGA, and which is, I think, now belong to Intel, and they will have a corresponding synthesis software. So when you buy this chip, they will provide you that synthesis software, where you can give the tested Verilog input into that synthesis software, and then that synthesis software will be able to make a circuitry which can be directly mapped onto their device. Okay, but if you take synthesis software due to say other company like Xilinx, and then you generate a circuit, it will work for their chips. Okay, it will not work for say Intel's Ultra chip. Okay, so that's the thing. So you need to have corresponding synthesis software if you are going to plan to implement or configure your circuitry in an FPGA or a CPLD chip. Now the other diversion you can go for is like, I don't want to use any of this standard architecture and implement my circuit inside that by configuring it, but I want to do my own chip design. Okay, so which is what is called as ASIC. So ASIC means application specific IC integrated circuit.